For part three of this presentation, we are going to be talking about the parametric effects on spin states of metal complexes.
When we talk about metal complexes, the electrons of interest are going to be in d orbitals, which come in different shapes. And a consequence of these different shapes is that some of them are going to be pushed closer to the ligands of the complex than others. So on that diagram at right, the ligands would be at the small gray circles. If they're closer, they're going to be repulsed more, and that gives them a higher energy. And then if they're these high energy and low energy states are separated by what's called a splitting energy, delta naught. If this splitting energy is smaller, we call it a high spin state because electrons are able to jump into those higher energy levels even though they are higher. And because of that, their spins, we'll see a little bit later, their spins aren't going to cancel out, so the spin is high. Conversely, if the energy is low, the electrons have to go in the bottom row where they're going to cancel out spins.
Oxidation state is one parameter that affects the spin state. It determines the magnitude of the splitting energy for metal alkyl complex. The cobalt-2 hexahydrate ion is high spin and weak field. Cobalt-3 hexahydrate ion is low spin. As the oxidation state increase for a given metal, the magnitude of the delta increase. So a V3 plus complex will have a large delta than a V2 plus complex for a given set of ligands. As the difference in charge density allows the ligands to be closer to a V3 plus ion than to a V2 plus ion. The smaller distance between the ligand and the metal ion results in large delta because the ligand and the metal electrons are close together and then they repel more.
The next parameter that affects spin states is the row number of the metal core. And the reason is kind of cut and dry. As we get lower and lower in the rows of the periodic table, we're going to have larger metals. And that means that just by default, their electrons are going to be pushed closer to the ligands, which means that the delta energy is going to be greater. And so we're more likely to have low spin states. In this experiment, we only looked at one row, but we also saw, based on that table on the bottom, correlation between how metals wanted to kind of organize their electrons by group as well.
Okay, field strength of ligand. The number of unpaired electrons in the ligand can be helpful to identify the spin states. There is a ranking between ligands. One of them are weak field ligands and other are strong field ligands. For example, the strong field ligands, the carbon monoxide or cyanide, they are strong sigma donor or strong pi acceptors, and thus can cause larger splitting. So, for example, the weak field ligands like fluorine or hydroxide can cause a small field splitting. Therefore, it can produce higher spin states. On the other hand, the strong field ligand can cause a larger field splitting. Therefore, it can produce low spin states.
Okay, so what affects spin state? The oxidation state of the metal, the period/group of the metal, and the field strength of the ligand. We would like to thank the Fresno State College of Science and Mathematics, the Core Space Undergraduate Research Experience Initiative, and for the technical staff, Douglas, Alan, Ian, and Maria. And finally, Dr. Ichuda and Chem 124 students.